Let's learn about multicollinearity, specifically how to detect multicollinearity using variance inflation factor. So let's start with the idea of multicollinearity. So having highly correlated predictor variables, highly correlated predictors increases the standard error of those predictors' coefficients. Let's hashtag advance. This is definitely an advanced topic. So having highly correlated predictors increases the standard errors of those predictors' coefficients, sometimes to the point where they actually flip the sign of the coefficient. And by flipping a sign, I mean sometimes the coefficient is positive, sometimes it's negative. So that's the idea. Let's go to an example. Let's say we're trying to predict the cost of, let's say, clothing. And it's going to be based on size, let's say material, whether it's name brand, and let's say popularity. Let's say size comes in, let's keep it simple. Let's say kid size, teen size, adult size. And let's say material is, I don't know, cotton, silk. Let's say name brand is an indicator variable on whether it's top 100 fashion brands. And for popularity, let's say we're measuring popularity by, say, number of Instagram followers. So that's our example scenario. And just as a preview, name brand and popularity are going to be very collinear because they're going to be very correlated with each other. Name brands tend to be very popular, and popular brands tend to be name brand. So what is variance inflation factor? What is this calculation? So the variance inflation factor, the idea here is you're going to regress each predictor against the others. Each predictor on the other predictors. And the formula for variance inflation factor is going to be 1 divided by 1 minus r squared. Anything above 5 is an indicator of multicollinearity. Anything above 10 is going to be high multicollinearity. So this calculation says regress each predictor on the other predictors. So let's have our first example, which is going to be size. And we're going to regress that on material plus name brand plus popularity. And then we're probably not going to find collinearity here. So let's move on to the one that's susceptible to multicollinearity, which is going to be name brand. And we're going to regress it on the other, so we're going to regress it on size plus material plus popularity. And let's say from this regression, we find that r squared is equal to 0.9. So we plug in 0.9 into our VIF equation. Our VIF will end up being, let's see, 1 minus 0.9, that's 0.1, 1 divided by 0.1, it actually comes out to be 10. So this is actually going to be an indicator of high multicollinearity. So what's the result? The result of that is the coefficients on the collinear variables, which is going to be name brand and popularity. So name brand and popularity will have very high standard deviations or standard errors. We'll have large standard errors. And they might even flip signs as a result. Flip signs, maybe. Since they're so related, we can't tell if the relationship is due to name brand or popularity. So it ends up getting very high standard errors. And it can flip the sign because sometimes, hey, because it's such a high standard deviation, it covers both the positive proportion as well as the negative portion. So what are resolutions for multicollinearity? So resolution, 1, you can drop one of the collinear variables. Drop one of the collinear variables. 2, you can collapse the variables. So take the two variables, collapse them into one. For example, using principal components analysis, or doing something easier like adding up scaled versions of the variables. And then 3, there are regularization techniques, for example, lasso or ridge, which we'll probably cover in a different video. So just to recap, multicollinearity, specifically how to measure and detect multicollinearity, uses something called the variance inflation factor. General idea is having highly correlated predictor variables increases the standard errors of all your coefficients. So how do we figure out whether they're highly correlated or not? What we end up doing is regressing each predictor on the other predictors. If they end up having very high correlation, then these individual regressions will give a very high R-squared. So in this example, when we regress name brand on the other regressors, including popularity, since that's a strong correlation with name brand, it gave a very high R-squared, 0.9. The variance inflation factor came out to be 10, which is super high. So this is a very key sign, telltale sign of multicollinearity, having very high correlation, indicated by this R-squared. So as a result of having both of these collinear variables, we're going to have very large standard errors for name brand as well as popularity. And then ways to resolve this would be to drop one of the variables, drop either name brand or popularity, collapse them into a single variable somehow, perhaps using principal components or something easier like just adding them up or adding up scaled versions of them. And then third, something known as regularization, which is going to reduce the size of the coefficients. And we'll cover this in a separate video.